Elon Musk's vision for the next decade relies on a massive influx of hardware, millions of autonomous robo-taxis navigating our streets in sync with armies of humanoid robots handling our daily labor. But powering that level of physical automation across a multi-planetary civilization requires a volume of raw computing power that exceeds current global capacity. Currently, that ambition is hitting a physical wall. This map shows the path of a standard computer chip. Design happens in the US, fabrication takes place in Taiwan, and final packaging is scattered across the globe. Because the manufacturing process is spread across tens of thousands of miles, iterating on a new AI chip design takes months. This fragmented loop creates an unavoidable bottleneck for rapid development. Rather than buying chips from established giants like NVIDIA or TSMC, if he cannot reinvent how computer chips are physically manufactured, the computational weight of his automated empire will eventually crush it. To bypass the global bottleneck, Musk is scaling up from the Gigafactory to the TeraFab. While a giga represents 1 billion, Tera represents 1 trillion. This chart compares the current global AI compute capacity against the proposed output of this new facility. This towering bar represents a single TeraFab, pumping out 1 tera of computing power every year, roughly 50 times the current AI computing power of the entire world. The core strategy is total vertical integration, compressing the entire global supply chain into one massive facility in Texas. Inside this building, the entire process runs in a continuous loop. The teams will handle chip design, direct silicon fabrication, packaging, and final testing under one roof. By unifying these stages, the traditional industry timeline vanishes. Musk's engineers could tweak a chip design and hold the finished product in their hands in a matter of days rather than months. Operating at this speed allows Tesla to bypass the rest of the tech industry by removing the global middleman entirely. The TeraFab's output begins with heavy-duty Earth chips required to process video feeds for Tesla vehicles and to drive the movements of Optimus robots. While the cars and robots get the headlines, they account for only 20% of the factory's total production. The remaining 80% of this newly manufactured silicon is destined for orbit, using SpaceX's Starship. These chips will be launched as heavily shielded server racks. Once deployed, they will form a sprawling constellation of orbital data centers. Compute generates massive heat, requiring vast amounts of energy to cool on Earth. In the vacuum of space, that heat management is handled by the freezing environment itself. These arrays also have access to unfiltered solar energy that is 5 times stronger than what reaches the ground, providing a nearly limitless power supply. By leveraging the extreme physics of space, SpaceX is building the computational backbone required for a galactic civilization. Returning to manufacturing reality reveals the difficulty. Building a cutting-edge chip plant is an incredibly complex industrial process. Industry leaders like TSMC have spent decades and billions of dollars mastering lithography, using light to print complex circuits on silicon wafers. Neither Tesla nor SpaceX has ever printed silicon wafers at this microscopic scale. Designing a chip architecture is a separate discipline from physically manufacturing it. This line graph compares Musk's $25 billion TeraFab estimate against the $45 billion reality projected by Wall Street. This price tag represents a financial risk that could impact the stability of the entire Musk empire. This follows a familiar pattern. Identify a massive global bottleneck, ignore conventional wisdom, and build a massive unified machine to fix the problem. If Musk pulls this off, he controls the entire vertical future of AI, from silicon in the ground to data centers in the sky. If he fails, it becomes one of the most expensive craters in corporate history.